right. So we're in section 3.3.
Yeah, and then we found it.
So when we talked about logarithms yesterday, we said that logarithms and exponential functions were inverses of each other, and what that told us is that y equals log base a of x. We said if and only if a to the y equals x. So we talked about logarithmic form and exponential form. So I want to circle this. Here's our y, and here's our y. Logarithms are exponents. So the y is the exponent. And we talked about that when we were thinking about going back and forth from logarithmic form to exponential form. We were thinking about the exponent. So logarithms are exponents. And our properties of logarithms come from the fact that they are exponents. So the way that we're going to work with them today comes from that fact. And the first thing I want to do is, so we're going to kind of let that simmer for a little bit. We'll come back to this in just a little bit. First thing I want to do is talk about, someone asked yesterday, so in our calculator we can calculate log base 10 and the natural logarithm. We have a log base 10 button and a natural logarithm button. What if we want to figure out what the log base 3 of 18 is? We don't have a way to push a button in our calculator to figure that out. So that's what we want to talk about, how we calculate, how we find logarithms of different bases other than 10 and e. And that is the change of base formula. And we'll write the formula here, and then when we talk about our properties of logarithms, we'll show why the change of base formula works. So our change of base formula tells us that the log base a of x equals, we want to turn it into a base that we can calculate. Log base a of x equals the log base 10 of x over the log base 10 of a. And that is the same as the natural log of x divided by the natural log of a. So if we want to calculate log base a of x, we use this change of base formula. Log base 10 of x divided by log base 10 of a, or the natural log of x divided by the natural log of a. And we'll talk in just a bit about why this works this way. So this gives us a way to calculate logs of any base we want. So let's look at a couple of examples. So let's say we want to find the log base 5 of 18. So we worked on some problems like this yesterday where we rewrote these in exponential form, or we used what we knew about the powers of our base. Well, 18 isn't a nice power of 5. 18 isn't the square root of 5. 18 isn't 5 squared. So it's not going to be something nice that we can figure out without a calculator. So we're going to use a change of base formula. So this is going to be log base 10 of 18 over the log base 10 of 5. And that's also going to be the natural log of 18 divided by the natural log of 5. If we plug that into our calculator, we get that this is approximately 1.7959. So what this tells us is, the other way that we could write that is 5 to the 1.7959 power is about 18. This gives us a way to calculate this. So let's look at another one really quickly. Change of base formulas is pretty easy. Log base 2 of 42. 42 isn't a nice even power of 2. So we can't just figure it out by what power of 2 this is. So we're going to use our change of base formula. Log base 10 of 42 over the log base 10 of 2. That is the same as the natural log of 42 divided by the natural log of 2. And if we calculate that out, we get that's about 5.3923. And if we try it out, we would see that 2 to the 5.3923 is about 42. And this also gives us a way of graphing logarithmic functions. So say we wanted to graph log base 7 of x, y equals log base 7 of x. And we wanted a graph of that. We wanted to plug that into our calculator and look at a graph. Well, our calculator won't graph log base 7, so we're going to say, use our change of base formula, y equals log x over log 7. Or we could use natural log x over a natural log of 7. And we could graph natural log x over natural log 7, or log base 10 of x over log base 10 of 7, and we would get our graph of log base 7 of x. So this gives us a way to graph logarithmic functions of bases other than 10 or e. So questions on change of base. We'll talk about why it works in just a second. Yeah.
Why would you ever want to use the natural log instead of the regular base 10 log calculator? You're going to do it?
Well, you usually see natural log in science and math versus the log base 10, but in terms of using them, they work out just the same. And I'll talk about log base 10 in just a second. Got a little bit of a historical note about logarithms. All right, so let's talk about our properties of logarithms. So these properties that we're going to write down come from the fact that logarithms are exponents. So for our properties of logarithms, for these we're saying that our base is positive. Our base doesn't equal 1. N is a real number. And we're going to use some different things. U and V are positive real numbers. So our properties. Because logarithms are exponents, log to the base a, log base a of u times v is log base a of u plus log base a of v. So if we think of properties of exponents, when we multiply two numbers raised to powers when we multiply two numbers with exponents, we add the exponents. Log base a of u divided by v is log base a of u minus log base a of v. When we divide two numbers raised to exponents, we subtract the exponents. So that's where this property comes from. And our third property, log base a of u to the n power is n log base a of u. When we raise an exponent to an exponent, we multiply the exponents. So logarithms turn multiplication into addition. They turn division into subtraction. They turn exponents into multiplication. And this is where they originally came from. Right around 1600, there was a gentleman, John Napier, who wasn't a mathematician. He did a job where he had to multiply large numbers. So he was tabulating tables and coming up with the entries to these tables, and he had to multiply large numbers, 7, 8, 9-digit numbers, 1600, multiply those large numbers by hand. So he was coming up with a way to simplify the multiplication of large numbers. And it was actually originally started from trigonometry. So he used trigonometry idea to simplify this. And he came up with this idea of a logarithm so that he could turn multiplication into addition. So that's where the idea of a logarithm came from, was to simplify this multiplication work. And the original base for logarithms was something like 10 to the 7 times 1 plus 1 over 10 to the 7. That was the base of the logarithm that the guy came up with. So imagine working with that base. You know, kind of a rough one. And the log base 10, the reason that log base 10 is called the common logarithm, we set up log base 10 so that the log of 1 is 0 and the log of 10 is 1. So that's why we call it, the way it was set up was so that the log of base 0 was 1, or the log of 0 was 1, and the log of 10 was, or the log of 1 was 0, and the log of 10 was 1. That's why those were set up that way. So anyway, there's our historical note. Logarithms turn multiplication into addition, division into subtraction, exponents into multiplication. Now I want to do some examples using these properties, but I want to show how the change of base formula comes from this property. So the change of base formula didn't just come out of thin air. It actually comes from this property. So let's say that y, so the change of base formula, why the change of base formula works. And when I was a student, I was glad I remembered this, because I could never remember exactly how the change of base formula. I couldn't remember the formula. I don't like remembering formulas. So it was easier for me to remember how it worked. So let's say we have y equals log base a of x. And let's rewrite this in exponential form. So if I rewrite this in exponential form, what do I get? A to the y equals x. That's what we started out by writing. Now what I'm going to do, just for this example, we'll use the common logarithm. I will take the log base 10. I'm just going to take the log base 10 of both sides. So I can take the log base 10 of both sides just like I can square both sides, just like I can divide both sides by the same number. So I'm going to say that log base 10 of a to the y equals log of x. Well, this last property of logarithms tells me that I can rewrite this y log a equals log x. I'm going to...
Mr. Beaver, 6:30, Moai Puck. BBA.
So now we're going to divide both sides by log a. So I get y equals log of x over log of a. Well, what did we start with y equaling? Y equals log base a of x. So I can say log base a of x equals log x over log a. And that is why the change of base formula works. So we just showed where the change of base formula comes from. It comes from this property. Kind of nice. All right, over here on the side, I want to write some common mistakes that I don't want you to make. Kind of like when we talked about trigonometry. There were some things with the trig identities that I didn't want you to do. So these mistakes, I don't want you to make these mistakes. So I'm going to say, don't do this. Log of x plus y does not equal log of x plus log of y. I can't distribute the logarithm. And the same thing for minus. I'm going to say plus or minus. So I can't distribute that logarithm. And I can't say that the log of x plus the log of y is the log of x plus y. This is the way that one works. The log of x times the log of y does not equal the log of x times y. I can't just combine these. I can't factor out the logarithm. And the log of x over log of y does not equal log of x over y. So I can't combine those logs. And this also does not equal log of x minus y. So we need to remember the way they work over here. Don't make these mistakes. All right, so let's look at some examples using how we might use these properties of logarithms. So where we're going with all of this is we want to start on Monday. We'll be solving exponential equations, and then we'll solve logarithmic equations, and we'll need these properties to solve our equations. So we want to practice using these properties. What we're going to do today is practice using the properties. So a couple of examples. So we want to expand. For our first example, we're going to expand log 2x to the third, y to the fourth. So we're going to use our properties of logarithms and expand this out. So first thing we're going to do is deal with all these things that are multiplied together. Logarithms turn multiplication into addition. So I can write this as log of 2 plus log of x to the third plus log y to the fourth. This one is as simple as we can get it. Logarithms turn exponents into multiplication. So we can write this as 3 log x plus 4 log y. And we've expanded this out as far as we can. So what we'll end up with is logarithmic equations where we expand these things out, and that will let us get, say, the log x by itself or the log y by itself in order to solve it. Questions there? All right, let's look at another one. The natural log of the square root of x plus 5 over y squared. We want to expand this. So let's deal with this division first. Logarithms turn division into subtraction. So natural log of x plus 5 minus the natural log of y squared. Square root of x plus 5, how can I think of square root of x plus 5 as an exponent? X plus 5 to the 1/2 power. So that 1/2 can come out front. Exponents turn into multiplication. 1/2 natural log of x plus 5 minus, and this exponent can come out front, 2 natural log y. Exponents turn into multiplication. And I've expanded this out now as far as I can go. So this is one tool that we'll use when we solve logarithmic equations, is expanding logarithms. So questions there? Yes.
On the first one, on the last line, just
Oh, I forgot. Yeah, no, the 2 is not supposed to be. Yeah, that reminds me. We shouldn't make this mistake. Or I wanted this to be a 2. Cancel out the logs and this equals 3/2. Can't do that. Where's my eraser? All right. The other kind of problem that we will want to do with our properties of logarithms is condense. So I'll go to another page. So we want to condense these logarithms. And the other way they'll ask the question, they'll say, rewrite the expression as the logarithm of a single quantity. So we have 2 log x minus 3 log y plus 1/2 log z. So we want to condense this, compress it as much as we can. So let's deal with these things that are multiplied in front. These that are multiplied in front turn into exponents. So I get log x squared minus log y to the 3rd plus log z to the 1/2. Subtraction turns into division. So I get, for these two, log of x squared over y to the 3rd plus log z, and I'm going to rewrite log z to the 1/2 as the square root of z. And then logarithms, addition becomes multiplication. So I get log x squared square root of z over y to the 3rd. And I've condensed it into the logarithm of a single quantity. So often when we get some kind of logarithmic quantity, we want to express it as kind of as compactly as we can. Yeah, John. Well, we could. So if we So yeah, we would need to listen. This would be, because if we did these two first, then we would end up with y cubed times z. So we need to do it in order. So we're following the order of operations. All right, let's look at one last one. We're going to condense. So we're going to condense 1/3. The quantity 2 natural log x minus 4 natural log y minus natural log of z plus 2. So let's leave this 1/3 out front. Let's deal with that last. We could put it inside, but we can deal with it last. So we're going to deal with our parentheses first. Now we're going to deal with our multiplication. So multiplication turns into exponents. So I get natural log x squared minus natural log y to the 4th minus natural log z plus 2. Now I'm going to go from left to right here. So 1/3. Natural log subtraction turns into division. And then I have subtraction again. So I have 1/3 natural log of x squared. And if I divide x squared y to the 4th by z plus 2, where does the z plus 2 go? Where does it go? On the bottom. And now what can I do with that 1/3? I have this 1/3 out in front of the natural log. It turns into an exponent, so we end up with a cube root. So we get the natural log of the cube root of x squared over y to the 4th times z plus 2. And we've condensed this down into the logarithm of a single quantity. So questions there? All right, so our homework, working with change of base and working with expanding and condensing logarithms. Page, what is this, 4? Oh, nope, that's geometry, sorry. 207. All right, were you messing with me again over there, Jackson, on the homework problems?
Maybe.
Maybe.
It's the new game.
Yeah, I do such a bad job of picking the numbers, I probably would never figure it out afterwards. And that could work out good or bad for you guys. EOE, every other even. EOO, every other odd. All right, there you go.